So we're the portable wheelchair ramp design group. I'm Davis England.
I'm Tanner Hesterman.
I'm Nick Miller.
I'm Andrew Campbell.
I'm Connor Head.
And I'm Spencer Kofed.
Okay, that's everyone there. So our project was presented to us by our advisor, Dr. Andrew Merriweather, as well as Dr. Jeff Rosenbluth, who works for UHealth, and for a program called the Trails Program, which they focus a lot on disabled individuals and allowing them to have a lot of capabilities. And they've worked on multiple projects designing these devices that will allow people that are in wheelchairs to ski and do other physical activities like that. But the project was presented to us, and it was kind of, it was really cool because it wasn't very defined when it was presented to us. They had a problem where they had looked at all of the wheelchair ramps on the market and realized that all of the wheelchair ramps were very heavy. They were difficult to transport, required multiple people to handle, and were actually kind of dangerous to handle because of pinch points and sharp edges. And so we kind of took this, and working with our advisor and with Dr. Rosenbluth, decided to focus on manual wheelchair users and to give them an opportunity to be more independent. And so the goal of this project was to create a ramp that would allow a manual wheelchair user to get up a couple of stairs and to use it, say, when he doesn't have a helper with them, or if they usually don't have a helper with them, it would allow them to go somewhere, say to a friend's house, and get inside without needing assistance.
And because a manual wheelchair user will have certain restrictions, we sat down at the beginning of the project and decided specific metrics that would guide our design process and help us to create a ramp that was usable for somebody in a wheelchair who didn't have extra help. The metrics that were most important in our design were weight, strength, and setup time. We wanted the ramp to weigh less than 25 pounds total, so a wheelchair user could lift, if they needed to, lift the ramp relatively easily, and especially we were focusing on a wheelchair user who had average strength and dexterity. We also wanted the ramp to support up to 500 pounds. And the reason for that was so if a wheelchair user needed somebody to help push them up the ramp, we wanted the ramp to be able to support both of those people at the same time. And we also really focused on the setup time of the ramp. This was important because we realized even if the ramp was collapsible and it was strong, if you weren't able to set it up in a reasonable amount of time, it didn't do a lot of good for anybody. So we focused a lot through testing and our design we focused on making a ramp that could be set up quickly and without a lot of trouble. We also wanted to keep our prototyping costs under $1,500 and also in the end be able to make a ramp that if it went to market was affordable for all wheelchair users.
So a ramp consists of kind of four main design components: the support rods, a couple of hinges, the support feet, and the slats. So as Andrew mentioned, we were trying to make a ramp under 25 pounds. So in keeping with that design metric, we decided to limit our length of the ramp to 6 feet. So the support rods, as you can see in the image in the middle, they run underneath the slats of the ramp. They're positioned 25 inches apart, because that is the average width of a wheelchair. The large wheels, the distance that is between them. When, excuse me, the 6-foot rods we cut into half, so they were 3-foot sections, and then joined them together with a hinge so that it was easily collapsible and a lot more portable, because that again was a very important design metric. That was portable, easy to set up, disassemble, and then it was lightweight. So originally we thought about using possibly carbon fiber rods. However, those were not cost effective, and the strength increase in strength was insignificant for the results we were seeking. So in the end, we decided to use 80-20 aluminum rods because we felt it was the best combination of both being lightweight as well as being strong. So as I previously mentioned, these 3-foot sections, well, they're 6 feet on both, 2 6-foot sections, but cut in half. They were joined together by a 304 stainless steel hinge that we designed ourselves and cut and welded together just to make it so it was collapsible and easy to maneuver for the user. If you'll notice in the picture in the middle, at the bottom end of the ramp, where the rods are sticking out, there's these 2 white feet protruding. Now, if you'll notice, it's kind of hard to see, but those feet are gently curved. So that curve is to allow the user to successfully place the ramp on in locations with varying heights so that it can adjust simply on that curved space. Those feet stick into the end of these 80-20 rods and are bolted into them, and they are currently made of PETG plastic filament. And finally, the slat design. As you can see in the ramp, there are 6 slats, and the width of each slat is approximately 12 inches, making up a total of 6 feet. We went through several iterations. Our first iteration, if you notice in the slat in the image, running across the middle of each slat, there's a rib. Our first design did not have that, and it had the strength we needed. However, in testing, we realized that it deflected far beyond what we desired, and it made the ramp seem very unstable for someone on it. So we tried to design with multiple ribs. However, the weight it added, as well as the strength, the increase in rigidity, was not worth it. So we opted for a single rib flat design, bringing together the final component of our ramp.
I'll be covering the analysis section of our design project. This involves Solidworks simulations, load testing, and user testing. In the preliminary stages of the slat design, we used finite element analysis in the Solidworks simulation tool to simulate the 500-pound load that we wanted to support. Now, once we found a design in Solidworks simulation that did not yield, we got this design manufactured, and then we started our first round of testing. Once we had the first iteration and started performing the testing, as Tanner had mentioned, there was a significant amount of deflection in this first slat. And so although it didn't yield, the deflection was quite high, and it was evident that we needed to increase the stiffness of this slat just so that we could decrease the total amount of deflection. The FEA models proved that they provided very accurate results based on the bent slat designs. For example, our third iteration for the calculated deflection and actual deflection measured during testing, there was only a 7% difference between those two. So this was very valuable for us because it proved that we could use finite element analysis to optimize the design of our slat so that we didn't have to do so many iterations through the manufacturing process. So we used Solidworks simulations to optimize the design of this slat. And as you can see in table 2, from design iteration 1 to design iteration 4, we were able to decrease the deflection by 55%. And that number is calculated off of the total deflection measured in or calculated in Solidworks simulation. Now, in addition to this load testing and Solidworks simulations that we had ran, we also performed user testing. Now, you can see the user testing times in table 3, and they do vary quite a bit. But if you take a look at user 4, it was a 2-minute 40-second setup time, and user 3 was 5 minutes and 10 seconds. So user 4 was somebody on our design team that had the most experience setting this up. And so what we learned from this is that with just a little bit of practice, you can greatly decrease the time it takes you to set up this ramp.
Yeah, so today I'm going to talk about the results that we saw from our project. And as Connor mentioned, we did a lot of work on the front end with the FEA and then individual slat testing to ensure that our ramp was going to meet the metrics before we assembled a complete prototype. And so when it came time that we found our 4th iteration was the one we wanted to run forward with, we found a manufacturing shop down in the valley and was able to work under the current restrictions. And then they were able to get the slats back to us. And once we had the slats, we then completely assembled our final prototype and were able to do the necessary user testing to prove feasibility of the project. The great part about our prototype was that it proved that we could achieve all of our design metrics. We came in at 21.2 pounds for the ramp overall, and we were able to support 500 pounds like our analysis had shown. As Connor mentioned, in table 3, the user testing did vary, but we all consider ourselves to be very amateur wheelchair users, and we believe that this group of people that use wheelchairs on a daily basis are probably much more skilled in the art. And we think that if we were able to give this ramp to them and let them experiment, they could essentially deploy and then retract this ramp on a much faster time frame or time scale than we could. But we were able to achieve our 5-minute metric, which was great. And then through all of our process of designing and then iterating, we spent $1,000, which was also under our metric. So all things considered, our design process worked, and we were able to build a ramp that turned out to be effective. And we were able to achieve positive feedback from the Dr. Rosenbluth and others that work with the wheelchair community. Now, what I'm going to do right now is switch to the video showing, just to give you an idea of what it looks like to deploy the ramp as an independent wheelchair user. And we can talk about questions later relating to this, but Spencer now is going to talk about further steps.
So all in all, we're pretty happy with where the ramp has come, but there's a couple next steps that we're looking forward to. A lot of those is just kind of ironing out those kinks that we've found through our testing, because we weren't able to do the user testing we wanted to do. And with that, we wanted to get some feedback and see where we can improve from a user standpoint. And then also one of the main things that we wanted to do is put a gripped abrasive coating on the ramp. And then this would reduce the noise because it's metal on metal, as you can see I'm putting it together here. And it's really loud. And so we ended up putting a liquid electrical tape type substance on it. If you can kind of see the black shadow where the metal rods insert. And then that'll reduce the noise even more. And it'll give it that grip for when you go downstairs. So behind him is 2 stairs. And at that point, it's pretty safe and comfortable to roll up it. But once you go to 3 on the way down, it becomes pretty slick with those finished aluminum surfaces. So we'd like to get a little bit more grip there. And then also later on in the video, you might notice the entrance to the ramp. There's a small little step up, and then the exit onto the surface. There's also a little gap. So we'd want to improve the gradual entrance and exit off the ramp. And then another option we were looking at was, so we met our design metrics and the capabilities of the ramp and kept it very light, but we wanted to look at maybe having a couple models of this ramp. So that way you could have someone maybe in a powered wheelchair or someone who wants a more heavy duty ramp and it'll weigh about like 30 pounds versus the 21 pounds. So we might have a couple different tiers of strength capabilities of our ramp. And then the last thing we were looking at was modularity. So like those gaps where the ridges are on the slats, you could attach railings or support rods to keep it from flexing even less. So there's a lot of options we're looking at to explore in the future.
Yeah,
And there's
any questions?
Yeah.
You can kind of watch the end of the video as you ask questions.
So is it done for the presentation?
Yeah, I think that's about it.
Okay, so then can you go
Yeah.
back to the like a poster?